Our guest of honor, Professor B.N. Goswami, SERB Distinguished Fellow, Department of Physics, Cotton University, respected chairpersons, deans, associate deans, HODs, and my dear faculty members and students. It is a glorious moment to extend my warm wishes on behalf of the research cell of Assam University that we have assembled here today for the Chancellor Lecture Series. Since this lecture series brushes upon inviting prominent scientists of the research to deliver lectures and interact with our faculty members so that it can develop the research culture at the university and improves the scientific knowledge of students and faculties to renew approaches and methodologies and make innovations in future. It is indeed a special privilege and pleasure to welcome Professor B.N. Goswami Sir, SERB Distinguished Fellow, Department of Physics, Cotton University, on behalf of Assam University, to this Chancellor's Lectures Series. Now, I would like to request our Honorable Vice Chancellor of Assam University to kindly felicitate Professor B.N. Goswami Sir. And I would like to request Dr. Bismita Chaudhary, Assistant Professor Computer Science Engineering, to kindly assist our Honorable Physicist to this dais. Thank you. Now I would like to request Professor Sunandan Barua, Dean Research, Dean Engineering and Technology, to kindly give a brief introduction speech to Professor B.N. Goswami sir.
Thank you, Nishant. Honorable Vice Chancellor, sir. Honorable Professor B.N. Goswami, sir, other distinguished guests present, dear colleagues, a very good afternoon to all of you. It gives me immense pleasure to get the opportunity to introduce someone who actually does not really need an introduction. We all know him. And if I have to keep on telling about the activities that is involved in the achievements, it will take a lot of time. But I will give out a very short introduction about Professor B.N. Goswami sir, and who has kindly consented to come over. And he informed me that it's actually the first time after the COVID pandemic that he has actually physically come to give a lecture, and we feel extremely honored for that. Thank you so much, sir. Come April, May, policymakers as well as farmers eagerly await the prediction of the Indian summer monsoon rainfall. For more than a century, however, prediction of the Indian monsoon remained a grand challenge problem, with skill of all models remaining subcritical. Heading the monsoon mission project of the Ministry of Arts Sciences, Professor Goswami changed the Indian monsoon prediction scene by helping to develop much improved coupled ocean atmosphere climate models at the Indian Institute of Tropical Meteorology, having high skill in monsoon prediction. Currently, Professor Goswami is a SERB Distinguished Fellow at Cotton University, Guwahati, after superannuating from the Indian Institute of Tropical Meteorology, Pune, as director. Prior to that, he was at the Indian Institute of Science, Bangalore, as professor and chair of the Center for Atmospheric and Oceanic Sciences. And after that, received his PhD in plasma physics from the Physical Research Laboratory, Ahmedabad. Starting to work on weather and climate science after his PhD, Professor Goswami spent 2 years at MIT Boston and 3 years at NASA ZFSC, that means the Goddard Space Flight Center, in Maryland, USA as postdoctoral fellow before returning to work in India in 1983. His research interests include understanding the variability and predictability of the Indian monsoon and how they are linked to other global predictable climate modes. He is also interested in how ocean-atmosphere interaction leads to climate variability and climate modeling. Professor Goswami has about 185 publications in high-impact peer-reviewed journals and books. In fact, he has publications in Nature also. It's like a dream for every researcher, scientist. High level of citations of Professor Goswami's publications is indication of impact of his work in the meteorological community. For example, his Indian Ocean Dipole Mode paper, published in Nature in 1999, is one of the 27 top cited papers from Indian institutions published between 1901 and 2014. Okay, that's over 100 years. 3 of his papers are cited more than 1,000 times. Professor Goswami has received numerous awards and honors, including the Santi Swarup Bhatnagar Prize in 1995. He is fellow of all 3 science academies of India, fellow of the Indian Meteorological Society, and fellow of the World Academy of Science, Trieste, Italy. He also received Kalapatti Ramanathan Medal from the Indian National Science Academy and the National Award in Science and Technology from the Ministry of Arts Sciences in 2014, and a Lifetime Achievement Award in Science and Technology by the government of Assam. So it's an immense pleasure that Sir is here with us, and without further delay, I would like to request Professor Goswami sir to come and deliver his lecture.
Thank you so much for that nice introduction, and I'm grateful to my good friend Dr. Talukdar for inviting me to come and give a talk here amongst you. I'm very glad to be here, and So I'm going to talk about climate emergencies. So it's basically a climate change problem, and I hope that I'll be able to give you a sense of why the climate has deteriorated so much that it has become an emergency situation today. So, so the climate, now where more and more people are realizing now that the climate has reached a kind of emergency situation. For example, some of the governments also have acknowledged that the climate has become really serious and we have to do something about it. But not that every government has done that. For example, last 4 years we have seen that United States government has refused to acknowledge that the climate change is serious. So they withdrew from the Paris Accord and so on. But fortunately, maybe next government will do something better. Similarly, the world, many other associations, medical associations and others are also recognize that situation is very serious. And in our recent, in our own region, we are experiencing over the last few years, if you notice, the floods have become more common and more intense everywhere else. For example, Bihar flood, whether it is a Kerala flood, Gujarat flood, Bihar flood, and in Assam, of course, we are always having floods, but the intensity and inundation has increased. So we know that is climate change is affecting all of us, and for example, this is Bihar flood last year, Assam flood, so many people died, and so on. So basically, climate change is essentially is a result of our own creation. It is basically a result of change in the environment by the humans, the exploding human population. If you see how the humans have grown and how the carbon dioxide increase in the atmosphere, which is the main cause of the climate change, and how carbon dioxide has increased, is very much correlated with how humans have grown. This is the human growth over the last 3 centuries, and of course in the last 1 century, 1.5 century, the human growth has exploded, started doubling and quadrupling much faster. And this is the increase of carbon dioxide and methane, and carbon dioxide and these other carbon in the population, they just go hand in hand. By doing this, we have changed the environment and the capacity of the earth to sustain vertebrate population, which 10,000 years ago, when the population was very small, it could do, it can sustain about 200 million tons of vertebrate population. At the time, the vertebrate population was just about that much, and so it could sustain. But after that, the vertebrate population has grown so much that it cannot sustain. So we are doing a lot of things to sustain ourselves. We are damaging the environment to the extent that the sustainability of the environment itself is degraded. So this is something that we must be aware of, and this is what is the main reason for. And once this environment degrades to a certain extent, it may be very difficult for it to come back and sustain. So the climate change, even though we don't see the big picture right now, it is a problem that is basically anthropogenic problem. It is caused by humans, and we must recognize and correct it ourselves. Unless we correct that, there is consequences can be very severe. So before going to the actual problem, let me see how. Give you an example of how humans are actually changing the earth or disturbing the earth. This has nothing to do with climate change, but I just saw this paper a month ago. Someone has published in Science. So this is, and the COVID had allowed us to see this picture, and this is a very amazing picture I see. What is plotted here is what is called, see, we're by doing a lot of heavy activity on the cars, like dynamites blowing, or very tankers going this way, that way, and it's a lot of heavy construction activity. All this is actually perturbing the earth, disturbing the earth, causing microseismic activity. So this microseismic activity then propagates, and you can record them. So everywhere there is a seismogram, microseismic activity is recorded. And you can always see that normally it just kind of lights up. This is the intensity of the microseismic activity. There are some 400 stations all over the world, including our Ceylon somewhere here. Okay, so all these amplitude of the microseismic activity, the color shows that activity is very high, significant. They are not very strong. They are not like 4.5 or 5 or 6 or Richter scale. They may be 1 or 2 in the Richter scale. But these are also important for various reasons. But it is actually, that means that it is shaking up the earth. All this activity is shaking up the earth, and so it is producing this seismic activity. So this shaking is quite serious. When it is complete shutdown was there during COVID, it just became dark. So it's just gone down. So this is how we are doing, modifying shaking the earth all the time. We don't realize that. So, and in fact, as soon as this lockdown started, just microseismic activity was just not there. And when it started back again, it started all over again. So it's like, it's an interesting example of how we are shaking the earth. So this is only in a physical sense, but in a variety of other senses, we are changing the environment. What this climate change is doing, of course, is changing various things in our environment, or causing the changes in the regional climate. For example, it is changing the sea ice over the over the Arctic. So the sea ice has a certain amount of cover. Every winter, the ice freezes up and it covers up a large area. It has a lot of impact in the climate. I can talk about that. But as the temperature increases, the sea ice does not form. The less sea ice form. And today, this, especially in this time, in the northern hemisphere, it is a minimum. This minimum is decreased significantly in the last few years, or last few decade or so. And so every time, it is now almost sometimes the ice is not there. During the summer months, the ships can go without breaking it. You don't need an icebreaker to go to the port today, because there will be a lot of paths which are open up. So this has had immense impact on the ecosystem of this in that region. But similarly, the Greenland ice. This is a big. Currently, today we are in a what you call one period of the Earth's history. This is called interglacial. Where the ice sheets are very small. It's confined only over the Greenland. But that Greenland ice mass is also now decreasing significantly by a serious factor. It is decreasing over the last decades. So once this ice decreases, then that melts and the fresh water goes into the ocean. Sea level rises, and that is how slowly our sea level will go up. Because in the last glacial period, about 20,000 years ago, our sea level was almost 130 meters below, and now it has gone down. Now, if this is melts up, it will again rise up all over the world, and a lot of people will have serious problems. Of course, let me go ahead. So this is the recent, very recent Arctic sea ice extent this year. Other thing that is happening is the polar regions are warming so much. Now, look at last year. Last year was a really very heavy, one of the warmest years so far. And this is the mean temperature anomaly. So that much about this whole region of the Arctic had more than 7.5 degrees above normal temperatures, persisting over a whole season, and that can have a significant effect. And this is, and what is happening because of that, the fires are increasing in the Siberia, and these fires are now the peatlands where there are a lot of what you call in the Arctic region. There is something called a lot of peatlands where ice. Normally it is covered by ice. The land is covered by ice. But then when the temperature grows, the ice sort of melts. So it exposes a lot of organic matter which is buried under ice. That organic matter produces methane, and then methane easily gets burned. So this sort of lot of fires have started in these peatlands over the whole region, and this is becoming now. What is happening is it is now producing more carbon dioxide and methane into the atmosphere. Already we have loaded the atmosphere with a lot of carbon dioxide and methane, and this process is now adding to the greenhouse gases in the atmosphere, and so it is taking. So these are the things that are sort of going towards a runaway greenhouse effect. So I'll come back to that. So what I'm going to do is just talk about how can we quantify this climate change. And then I'll talk about a little bit about the science of the climate change, how we can estimate and why it has happened. Then finally, we'll talk about some about adaptation and mitigation. So the climate change is there, and the way that we are going, it's not going to stop tomorrow. At least it will take 100 years, and by that time already the situation will be much worse. So what we have to do is to prepare ourselves to adapt. How can we adapt? So the adaptation is the key, and for that we have to learn how we can adapt to various different calamities. Or So at the end of this, so if I have time, I will try to go through two problems that I want to highlight. For the Northeast, there are two important problems that we need to adapt. One is of course the flood. Floods are going to be more intense, more frequent, and we have to live with it. And how can we adapt to it? And so what we need to do to adapt it. Second is, of course, the biodiversity in this region is a very key resource for sustainable development. And this key resource is shrinking, and biodiversity is shrinking very badly in this region, and therefore, what can we do to prevent and how to, for sustainable development, what we need to do. So something, if I and what kind of research that we might need to do, I'll come back to that at the end. Okay, so what is climate change? Climate change is nothing but the global temperature increase. The last 100 years or so, the global mean temperature has increased by about a degree. So this is the global mean temperature, the average of temperatures over land and ocean properly weighted over the whole year. Because normally the temperatures in one hemisphere is warmer, another hemisphere is colder. So you cannot do in one season, because then you have to average it over both seasons. And so it is like a yearly average. and then taking the baseline around pre-industrial time, the temperatures have increased by this much, about 80. And these indicate certain amount of uncertainty that observations may have different sets of data. But there is considerable amount of consistency in this increase, and this we have great confidence now today that temperature increase is very real. And why it has happened? It has happened because of this greenhouse gases. This is the growth of the carbon dioxide. The measurement of carbon dioxide in Mauna Loa. Carbon dioxide is a very long-lived gas. It is inert gas, so it lives in the atmosphere for a long time. So once it is put in the atmosphere, it gets mixed up, well mixed up. So observations in anywhere in the world will actually have a mean background. Anywhere, one measurement itself is good enough. But of course, the seasonal cycle may be different in different places. But well-mixed carbon dioxide measured in Mauna Loa gives a very good example. This one, very good estimate of how much carbon dioxide, how the carbon dioxide has increased. This is the increase of the methane, which is another greenhouse gas, which is highly potent, but the concentration is small. So this concentration is like, today we have about 414 parts per million in the atmosphere, and methane is like, today we have about 1850 parts per billion in the atmosphere. So these are the kind of numbers that we have. I'll come back to that, what is the significance of these. So if you look at how are these numbers really serious? Why are you talking about it? In fact, they are quite serious, because if you look at our last 1 million years, or even last 3 million years, this is a record of methane and carbon dioxide and global change of temperature in the last 800,000 years. This record is coming from the ice cores from the Antarctica. Antarctica ice has been accumulating over the whole last million years. And from the ice cores, you can actually find out, you can dig an ice core, and then from the core, there are some air bubbles inside. From those air bubbles, you can actually measure how much carbon dioxide was there. And then you can date it. So you can actually find out how much carbon dioxide was there, how much methane was there, how much dust particles were there, etc., etc. And people have done that. This is, it turns out that we have gone through these variations of carbon dioxide where like 260 to 280, it went up to 200 to 280 parts per million. It never became higher, and they have gone through these ice ages. There are ice ages and the interglacial period, and about 8 cycles of that has gone through, and carbon dioxide is never more than 280 parts per million. And today we have 414 parts per million, which is almost 40% larger than that, and so it is extraordinarily high. And the last 3 million years, there is no record of such. So therefore, we are significantly changing the constituents of the atmosphere, and that has an impact on the climate. So this is the important part. So the current level of greenhouse effect is unprecedented in the last 3 million years. Maybe 65 million years ago there was enough 50 million years ago there was, but the climate was very different. So who has contributed to this? And it is an interesting figure. So here, what is this is about 1900. We had in the atmosphere about 2 gigatons of carbon dioxide. Okay, in the atmosphere, and today we have about 37 gigatons of carbon dioxide in the atmosphere. It has increased from year to year. And different countries have contributed to it. How they have contributed to it? Over the years, it's shown in this chart, where China has started contributing largely from about 50s or 60s, and now today they contribute a very large fraction of the total. Very large fraction of the total. United States, they started contributing to this all the way back in 1900, beginning of the 20th century, and contributed significantly throughout the period, still contributing significantly today. This is European nation also did. So the European nation and US, these are 2 major contributors, and they already put up enough carbon dioxide by 1950s when India and China only started. By that time, already the atmosphere was damaged to great extent. And India is here. India has very little contribution until about 80s, and then only we have started. Today we have about 7% contribution to the total, which is not insignificant, but nothing to compare with those nations. But we still need to contribute less. We have to somehow do. But because we are a developing country, rightfully our government has not agreed to cut down earlier. But recently, in the last 5 years, we have agreed to cut down carbon dioxide emission significantly, and I think today we are doing reasonably well. This is Russia. Russia is also like our India, but they started a little earlier, and other countries. So I want to. So I think this is something interesting, important point that the countries, the developed countries, forget that they have actually caused problem to the rest of the world long before the rest of the world started contributing to it. But if you look at this problem as a per capita problem, because energy consumption is actually related to the population, as per capita, our population is high, and we put it less carbon. Put some carbon dioxide. So per person we are putting much smaller compared to United States, for example, or even Saudi Arabia. There also population is less, but they are using so much energy, and they are putting more carbon per person. So we can argue that we are not doing too badly because our population is high and we are not putting as much as the others are. But that is not really a good argument. So how does it work? Why does it affect this? So basically, if the carbon dioxide is there, how does it affect the climate? So that is essentially due to this is a very simple problem of radiation balance. How the temperature of the atmosphere of the Earth is affected by our climate is essentially a result of how much energy we are getting from the sun and how much energy we are losing. The Earth is also like a black body; it is radiating, but we are getting some energy from the sun. And if there is a balance of energy, then the Earth will come up. If there is a deficit of energy, then Earth will cool down. And so that is the basic simple principle. At some level, the climate change or the science of climate change is very simple. It's basically energy balance, basic energy balance, in which the incoming solar radiation is intercepted by Earth, and that much, so this unit, this is called solar constant. That much energy per unit area is coming to Earth, and this disk of the Earth, which is radius r, it intercepts that much. A fraction alpha is then reflected back, and so this much energy is absorbed by the Earth and atmosphere system. And then it radiates like a black body radiation. So black body radiation is radiation is emitted all over the surface, so it is 4 pi r square. And this is called the Stephen-Boltzmann law. If a particular body has a temperature T, it radiates as a 4th power of the temperature, at the rate of 4th power of the temperature. And this is a constant, Stephen-Boltzmann constant. And this parameter is what is called transmissibility. Now, Earth will radiate like a black body at certain wavelength, but that radiation has to go to the space or be lost. Is it lost or trapped in the atmosphere? So, if the atmosphere is not there, everything that is radiated will go to space. So, we can balance easily. But since there is an atmosphere, only a fraction of the radiation may go to space. So, let us say that the tau fraction of the radiated energy leaves to the space. So, then that much is what is lost is balanced by what is gained, and that gives me a temperature, equilibrium temperature. Now, this transmissibility of the energy is dependent on the constituents. How much energy is lost, it depends on what is there. In our atmosphere, we have these carbon dioxide, water vapor. These are constituents which can absorb long wave radiation. So, our temperature being at around 300 degrees Kelvin, it radiates at what we call long wave. The wavelength is like about 10 microns or more. So, at that temperature, there is a lot of absorption bands in the atmosphere, atmospheric constituents due to carbon dioxide and water vapor. And those things absorb a fraction of that radiation, and therefore only a certain fraction gets lost in space. So this transmissibility is affected by the constituents, and if you are modifying the constituents like carbon dioxide, then it is also changing the transmissibility. That change in the transmissibility will change the equilibrium temperature, and that is how our temperature gets increased, because we have reduced the transmissibility. So the temperature has to increase to make balance between incoming and outgoing radiation. And then if we do that, if we had done a simple calculation, suppose my transmissibility was not there, there was no atmosphere, what would have happened to our mean temperature? If there was no atmosphere in the atmosphere, everything that Earth was radiating would just get lost to the space. So that means, if I balance that, then I get a temperature which is minus 18 degrees Celsius. Global mean temperature will be, if there is no atmosphere, the global mean temperature will be minus 18 degrees Celsius, which is like then everything will be frozen and there will be no life on Earth. So the atmosphere is a natural source of greenhouse effect. Atmosphere has a natural greenhouse effect which makes the atmosphere warm, the Earth warm by about 33 degrees. As a result, it has become habitable and everything can sustain. But now, by increasing the carbon dioxide, we are changing that to the extent that temperature has to increase by 1 degree more to balance it, and that is what has happened. So this is a very simple energy balance which explains the atmosphere of Venus as well as Mars, depending on what kind of atmosphere they have and how much radiation they get from sun. That gives us the surface temperature of Venus is closer to the Earth, closer to the Sun, but it has very high albedo. By the way, the Earth's albedo is the reflective part is about 30% of the radiation gets reflected back, 0.3, because of the clouds, ice, etc. 30% of the solar radiation that comes out is reflected back. But in Venus, they have maybe 80% of the reflected, because they have a thick carbon dioxide cloud. Okay, so but because of that, but also the Venus, because there is a lot of carbon dioxide in the Venus, so the greenhouse effect is also very strong. So small amount of radiation comes in, but it cannot escape. So it keeps on increasing the temperature. So the surface temperature increases to this much, so that only that fraction that leaves is balances what is absorbed. So that way you can actually understand the climate of all the planets. So the other challenges, but these are the simple part of it, but the challenge is to understand clearly how much exactly will change, how much temperature exactly will change will depend on a lot of internal processes in the atmosphere. Roughly we can say that okay, it has to change about 1 degree in a very simple back of the envelope calculation. But to actually calculate, we have to take into account the effect of the clouds in the atmosphere. And the clouds, because clouds not only reflect energy, but it also releases certain amount of energy within the system. The latent heat that it stores, it releases. So it affects the heat balance in the atmosphere significantly. So we cannot do without clouds. And therefore, but the clouds are very complex, and clouds have a multi-scales. So the cloud starts, to form clouds you need condensation nuclei which are very small, 10 to the -8. Then they make it to individual clouds over about a kilometer. Then they get organized into clouds of tropical cyclones like about 1,000 kilometers. All these tropical cyclones then get organized into the large scale systems like called intertropical convergence zone, which are like 10,000 kilometers. And everywhere the heat is released, and then solar energy is also reflected. So it affects the heat balance. The clouds affect the heat balance significantly within the system. And unless we can predict or simulate the clouds correctly in a model, we will not be able to exactly heat balance. And that is what is one of the serious problems in our climate model, because it involves the scales, starting from very small scale to very large scales, ranging for about 15 orders of magnitude. It's a very huge problem, and that is one of the biggest problems in modeling, because we have the small scales we cannot resolve in the models, we have to somehow parameterize. The parameterize means some approximation has to be made, so system is not complete. Our models cannot be exactly perfect because we have to make some approximation to make this. Clouds, different types of clouds are there. The icy clouds allow solar radiation to come in, but does not let the long radiation to go out. So it lets more solar radiation to come in and but traps more longer radiation. On the low level clouds, the low level clouds on the other hand are more thick, they have big water drops. The water drops, big water drops are more shiny, they reflect more, let less solar radiation to come in, but it allows more longer radiation to go out. So the different clouds affect this balance differently, and therefore we have to calculate that. Also, the clouds have a feedback which affect the greenhouse effect. For example, the increasing carbon dioxide will increase global warming, increase the temperature of the earth. Temperature of the earth will increase the evaporation. Evaporation will have more clouds. More clouds will have more reflectivity. More reflectivity will try to produce cooling. So there is a negative feedback. But there is also a positive feedback associated with the clouds. The clouds increase global mean temperature, increase water vapor, but not only clouds, there is increased water vapor in the atmosphere. Increased water vapor has increased greenhouse effect because they can absorb longer radiation. So it will try to warm the earth. So depending on the distribution of the clouds, we have to estimate what is the net effect of the clouds. Whether it will be warming or the cooling is something that predict offhand. We have to calculate it very seriously, and we have to do that. We have to realistically simulate the clouds. So that is a serious issue. But that is one of the problems. I am not going to all the problems, but we should concern today because not only the problems of calculating this, but the climate system has a lot of tipping points. It is known that if you change the climate to a certain level, the forcing changes the climate to a particular point. It cannot come back again if you change the forcing. The forcing will then greenhouse gas. It can so happen that if you go on increasing the greenhouse gas, temperature will rise. At some point of time, it may have so happen that even if you cut down the greenhouse gas, temperature will not change. This is on the global scale, but on the regional scale, many things there are evidences that can happen, and this is our major concern. That can be seen from this diagram. This is sorry. I'm sorry. We have gone ahead of that ourselves. So this is the representation of the last 1 million years, the variation of the sea level in our over the whole world and the temperature change. This is during the glacial period, the interglacial period is here. That is one period today we are in. Today we are somewhere here. The temperature is here. The sea level is also a little bit high, but during last 1 million years, there were several glacial periods where the sea level was low, temperature was low, and then it came back and became one period where there is interglacial, where sea level was high and the temperature was high. But today's temperature is larger than any of the last interglacial periods over the last 1 million years. So we already have crossed that. Now, with all the modeling efforts, we can see that if we increase the temperature, if I cut down, if we do some intervention like cutting down completely carbon dioxide and etc., we may be able to try to bring the temperature back. Unless we do that, so this is the part like, if today we have so much of carbon dioxide that is going on, so much of emission is going on, if we can cut down by substantially, that is the goal of the Paris Accord, by 2030, we should cut it down to 50%. And that if we do, maybe we will be, but even that is questionable. But if we don't do that, if it crosses this level, what will happen is that more ice will melt, so reflectivity will be less, more solar radiation will be absorbed, then more methane and carbon dioxide will be emitted because of the peatlands, from the peatlands. As a result, more and more carbon dioxide, more stronger greenhouse effect, and it will become a runaway greenhouse effect. And then the temperature may rise all the way by about 10 degrees. And that was like 55 million years ago when our temperature, when the world temperature was like about 10 degrees more than today. And then there was no ice anywhere. And so the species will have a lot of difficulty, everything will change. So that is it, we are already in that tipping point. So unless we do something very drastically, the climate is going to go through a tipping point and then may be impossible to come back. That is the major concern today. And this is actually happening already, as I mentioned during the lunchtime. So the biodiversity, the species extinction rate in the last 100 years has changed by 10 to 100 times the background rate which prevailed over the last 1,000 or 2,000 or 10,000. So that also the species is already extinct. Some species going, some species coming up. So there is a balance. There is a certain amount of extinction rate, but the rate at which the species extinction is taking place is far larger today. Therefore, it is now assumed that it's almost sure that we are heading towards what is called the sixth mass extinction. And there are several papers that now have documented this. So this is the another major concern. And this has to do with the human population, as I said in the beginning. In fact, this has to do with this 10,000 years ago. If you see, total out of the total vertebrate population, only 1% was human. 10,000 years ago, we have very little human, right? It's the last 10,000 years only. It is the whole evolution, how we have changed the environment, just 10,000 years. And of course, only last 200 years, it was the worst kind of change. And this is very amazing. So, for today, you see, humans contribute to 32% of all vertebrates. And the wild animals, which used to be 99%, has gone down to only 1% today, wild vertebrates. Okay, and but vertebrate, total vertebrate is quite high, but what is the other 67%? This is livestock. Livestock is only to serve the humans. Because to give you food, to give you meat, milk, or transport, whatever, that's only to serve the humans. We have increased livestock. So this is a very serious problem. So now sustainability has become a serious question because of this. So what I am worried about is that all the mass extinctions in the past, these 5 mass extinctions that we have talked about, were all by natural cause, either by meteorite hitting or something happening, or volcanoes active in the volcanoes in this very active volcano produce a lot of things in the atmosphere and change the environment. But today it is not by any of these natural things, it is by humans. And the humans we cannot predict, and because they are very selfish and they are greedy. And so this is what makes it very, very serious concern. In fact, COVID apparently is actually accelerating the mass extinction because is an example of mass extinction. This is a paper which just came out June recently. They show some evidence that the COVID is actually helping to increase the mass extinction in some way. I am not very sure about the details, but interesting study. So, if the temperature increases, what will happen? The vulnerability of various parts of the world will change, and India will be the worst hit. This is the worst case I have seen. I have other figures I left out. So, this vulnerability is based on several different exposures, heat wave exposure, water stress. Water stress will increase the risk of power production. The crop will change, will change, habitat degradation will change, and all that if you put together into some kind of a number, risk score. That risk score in India, because of our population, because we are highly populated, we are also more at risk, and our resources are less. But we are more vulnerable. So we have to be very careful. Even if somebody is not doing what they need to do, we need to do our part to control this. So, unless today this is how the temperature is going increasing, and in this unless if we continue to global emissions are increasing this way, if we continue to increase and bring it down by 2030 to half its value, then we may be able to contain it to about 2 degrees centigrade by the end of the century. But if we don't do that, we will not be able to control it. But right now, it appears that is not going to happen. Because already we have put in the last couple of years also, we have put in last 4 years, we have put in much more because of the American problem also. We have put in much more in the atmosphere then it will take longer time to actually recover. So in India, what is happening? So we have estimated, we have done some studies to our summer monsoon, and we have shown that I don't want to go into great details, but what is that? In India, actually, total amount of rainfall, this is the year-to-year variation of rainfall, and over the last almost 200 years. Fortunately, if you see, there is not much of a trend. Indian monsoon is somewhat stable. There is no big trend either way, either increasing or decreasing. Actually, we expected a very large increase in the because as the temperature increases, the atmosphere is moisture holding capacity of the atmosphere increases. This is the Clausius-Clapeyron relation. So that the saturation vapor pressure increases, therefore it can retain more moisture. So, as per degree increase, there is 7% increase in the moisture in the atmosphere. So, if the 7% increase has taken place, so that moisture, if it rains, therefore there is 7% increase in the rain, but it's not happening. Something is interesting. This appears that people are saying that this is because of the pollution, because we have recently a lot of pollution, but I don't believe that. That is a kind of a view, because already 300 or 200 years data also we are not seeing any. There is a lot of natural variability. It has multi-decadal variability. Monsoon has multi-decadal variability. We are not able to find this trend from the multi-decadal variability. People have not found that. What we need is, we found that trend. The trend is small, but it produces about 3% increase instead of 7%, 3% increase per degree increase of temperature. So there is some small increase in the rainfall. But most interestingly, it increases the extreme events. So this is a paper we published several years ago in Science, where it showed that the heavy rainfall events in India have increased by about 50% over the last 50 years. So the number of heavy events, and that's already a big signal, because unfortunately, it was not very well, people have not taken heed to it. But today we are feeling that because of these extreme events are producing the flash floods and the flooding intensities, etc. So these are the events that are responsible for floods. And in the expense of what we call low and moderate events. Low and moderate rainfall events are decreasing, the extreme events are increasing. This is actually affecting our region very, very badly. Because the low and moderate events actually help us restore the groundwater, but they are decreasing. The groundwater is affecting, groundwater is depleting, it is not getting discharged, but there is heavy events are pouring and they are draining out. So this is actually a very serious event. And the same thing is happening in the Northeast. We have another study which has just come out. Which in Northeast also happening that, but Northeast actually mean rainfall is decreasing. Mean rainfall is decreasing and extreme events are increasing. So we are even more at risk. So this point is that this is the extreme event intensity, how heavy these rainfall events are increasing at a rate which is 21% per degree centigrade, which is per degree Kelvin. That is per degree increase of global mean temperature. The intensity itself is increasing by 21%. That means that today the most heavy rainfall event is 20% higher bigger than that used to be 50 years ago. So that is also a serious problem, because this is what is causing the more severe floods, severe flash floods. This is larger than the 7% that is predicted by the Clausius factor, much larger, 3 times larger, and that is the serious issue. So this is summary of what we are having. So we have a serious problem, and we need to be really prepare ourselves how we will be protected from flash floods and this thing. So different the policy makers have to come up with ideas how we can adapt to this. This is an adaptation issue that is serious consideration. And in Northeast we have done this study has just come out with climate change. This was done at Cotton. We did over 24 stations in this region, which is 90 years of daily data. And from that we were able to show that the 99.5 percentile heavy events have also increased at the rate of about 12.5% per degree increase of temperature. So that is also very high. But the mean temperature, mean rainfall is decreasing at the rate of about 3% per day. So mean rainfall in the Northeast is decreasing. Overall in India, mean rainfall is increasing a little bit, but in Northeast, mean rainfall is decreasing. But extreme events are increasing in all over the place. And that has a dynamic behind it. Do something. Now what we can do is different from different. Individually, we can do something to cut down carbon footprint in the atmosphere by cutting down energy consumption, making more efficiency in the whatever product we do. But more than that, we have to but large change can come only through policy changes at the government level, like how we can larger like factories. So we must change all the coal-based factories to some green energy-based factories. So by solar or something. So we have to promote solar. Solar is the ultimate source. We have to promote. For that some investment is required. We must make investment. Convert all the coal-based to solar if possible. So and wind and others, whatever renewable sources of energy we have to extract. So the policy decisions are required. India is doing a lot of that, but that too. I must say that it is too little, too late. I mean, we have not done enough. But I think we need to do more. But India is actually, relatively, at this present time, India is doing reasonably well. But the point is that some of the policies are denialist, what I call denialist, the climate change denialist, this don't want to, and they expect, why they don't accept the climate change? They ask for a definite number. What will happen? Tell me. What will happen if 1 degree changes? Or what will happen? How much will temperature will change after 50 years or 100 years? My models cannot give you exact number, but because of the complexity I told you. But because they cannot give complex number, this is all humbug. This is not humbug, but I can tell you with great probability what is going to happen. And all the decisions must be made based on probability. You make all the decisions based on probability, even in your financial market. You make decisions on probability, but when it comes to climate change, you don't have to make decisions on probability. You want numbers. That is not possible. Nobody can give you numbers, exact numbers. But this is what hypocrisy that we have, and this is hypocrisy of humans. Again, I am coming back to that problem. So this is what we have to do, and we have to act. We have to act based on probability, and the probability can give you very high chance of what is going to happen because we know the science and we know. We have now models which are much more reliable, but the models cannot give you a deterministic number. Models can give you a probability, and the probability and the confidence, and that we can give you, and you have to make decisions based on that. And this is what is happening, and so this is something that I try to tell everybody. So we need to change this mindset, and to change the mindset, we have to make a movement. Everybody has to contribute. And a lot of people are coming up now today. Younger generation I see is very conscious. They know they are. This young lady has made a movement out of it. So she is very strong. Like that in India also there are a couple of young people who are very prominent in this. So I think a lot of young generation is coming. But so this movement is going to force the policymaker to change their attitude. I think that is what is the future. Okay. So how much time do you have? I think we have already passed. I can spend 5 minutes, 10 minutes. I'll focus on one problem then, not both the problems. So let me talk about the biodiversity problem then. The other problem I can talk about. So what I think is that. So one of the problems that I said in the beginning that we have to adaptation strategy we require for the groundwater flooding. The flooding is going to happen. Flooding is going to be with us, and we have to find strategy how to adapt to it. It will be more intense, more frequent. Now, unless we have a long-term view of how to adapt, life will be lost, property will be lost, and they will be most vulnerable people will be in the rural areas, they don't have a voice, they don't have any mechanism to cope with yourself. So we have to develop policies, and one of the policies that I have been telling is to give good forecast. The good forecast will prevent this loss. And the good forecast today of the floods 1 or 2 days, 1 day ahead. 1 day ahead is enough. 1 day ahead, a good forecast can be done by hydrological modeling, and with all the modeling and the forecast that is available for rainfall. Today rainfall, atmospheric science has now advanced to a level where you can give reasonable confidence the rainfall prediction up to 2 weeks in advance. Large scale, not individual details, but large scale amount of rainfall we can give up to 2 weeks in advance, and use that data to force these models and give a much more accurate forecast. And it can be done. And this has been demonstrated. But what I see that in our region, this policy is not being implemented properly, and we are not even recognizing this issue. The second thing that we must be associated with this to adopt is that we should build shelters. We should build shelters in the flood-prone areas, like cyclone shelters in other places, in Odisha. Tamil Nadu, Orissa, especially Orissa and Andhra Pradesh, they have built very nice. Today, cyclone forecasts are very, very accurate. As a result of the most severe cyclone, also no human loss, almost no human loss. 3 decades ago, or 2 decades, even 2 decades ago, the severe cyclone would cause 1,000 deaths in this. Today, we have almost in the last couple of years, we have so many big cyclones. Very little. That is because of 2 things. One is good forecast. Secondly, the shelters. As the people have to accept your forecast. They have to have confidence. Once they have the confidence, they will move from their vulnerable location to the shelters. This has happened. And this can happen in the flood-prone areas also. If we build shelters, and if the forecast of the skill of the hydrological forecast are good, which I can very well assume that it is possible to do that, because from the background that I know. So this is one issue that I'm not going to go into details of that, how it can be done. Let me just end with just saying a few things about the last problem that I wanted to talk about is the biodiversity. This biodiversity problem I don't know anything about, but I have an interest in understanding the climate change impact on the biodiversity in the region, because I want to understand. And when I did a little bit of investigation of what is available, what is not available, something that comes out and strikes me that there is very little data, there is very little work that has been done. And I had discussion with Dr. Talukdar, and it turns out that this is, I think, a gold mine, and there is a lot of importance, and it has a lot of implications in this, because this climate change of global mean temperature can influence the phenology, physiology, and distribution of species from different places, because different heights, vertically as well as horizontally, species can distribute differently, because like for example, I will give you an example. In Jammu and Kashmir, where apple is grown, earlier the apple used to be grown at a height which is lower, and today because of the temperature it goes to another height, because at that height the temperature has increased, so you can have the most good return only at a different temperature, different height. So like that, these things, phenology and everything changes with